For decades, human telepathy was strictly confined to science fiction. Now, artificial intelligence is reconstructing recognizable images and text straight from human brain scans. Historically, the human mind has operated as a perfect black box. Your thoughts, memories, and inner monologue were entirely private, locked away in a sanctuary inaccessible to the outside world. Recent headlines show a rapid shift in this reality. Researchers are successfully deploying algorithms that can correctly identify exactly what a person is looking at or thinking about, pulling clear data straight from their brainwaves. This raises an urgent question. Are these algorithms genuinely reading our minds, or is the public simply misunderstanding the mechanics of this technological leap? Separating dystopian panic from medical reality requires examining the technical architecture that allows a machine to map neural activity to specific meaning. Let's start with the biology. Your brain doesn't process thoughts in English sentences, and it doesn't store memories as perfectly formatted JPEG images. When we scan a brain, we aren't seeing thoughts at all. Scientific instruments can only measure indirect physical reactions, like electrical spikes picked up by an EEG or changes in blood flow tracked by an fMRI machine. These composite scans show chaotic, localized heat maps of neural activity, where the yellow and green zones represent spikes in blood flow. This raw biological data is incredibly dense and noisy, which is why it has historically been impossible to interpret as clear, distinct thoughts. For years, researchers faced a severe bottleneck. We could pinpoint exactly where activity was happening, but lacked the mathematical tools to decipher what that physical activity actually meant. Without a reliable way to translate this organic noise into a structured language, the scanner's data remains essentially useless. Artificial intelligence serves as the specialized pattern recognition engine needed to bridge this gap. These algorithms are designed to find the underlying structure within vast, chaotic biological datasets. To train this engine, researchers place a human subject inside an fMRI scanner, like the clinical machine shown here, and expose them to hundreds of hours of controlled media, such as specific podcasts or photographs. While the subject listens, the AI maps blood flow patterns directly against the media. Over time, it writes a personalized dictionary matching unique signatures to concepts. Finally, a probability chart calculates the highest statistical probability of what the brain is actually processing. What the general public calls telepathy is in reality a triumph of predictive statistical translation. Naturally, this capability sparks immediate fears of non-consensual surveillance by corporations or authoritarian governments tracking us on the street. But covert surveillance is physically impossible right now. Gathering this data absolutely requires a subject to lie perfectly still inside massive, immobile clinical machines that cost millions of dollars to operate. There is also a strict biological limitation. These AI models are not universal. To get any usable data, the algorithm must be trained for hours on one specific, highly cooperative individual to establish a functional baseline. Because of these severe hardware requirements and biological bottlenecks, involuntary weaponized telepathy remains strictly science fiction. While we don't have to worry about mind-reading surveillance, these breakthroughs offer profound, immediate benefits for the medical field. The primary use case right now is utilizing this predictive AI to act as a digital voice for individuals paralyzed by locked-in syndrome, allowing them to communicate using only their brain activity. As AI models become more efficient and imaging hardware moves from room-sized magnets toward portable devices, direct brain-computer interfaces will become highly practical. By building customized dictionaries for individual brain signals, researchers have proven that we can accurately translate thought into data. Predictive modeling has successfully mapped the relationship between organic noise and human meaning, establishing a functional, data-driven link between our biology and our machines.